So the first one is called CommonGraph, Graph Analytics on Evolving Data. And we have Nael Abu-Ghazaleh, who will be our speaker today. So Nael is a professor with the joint appointment at CSE and the ECE departments at UC Riverside and the director of the computer engineering program. His research interests include architecture support for security, high-performance computing architectures, and networking and distributed systems. So thanks.
Thank you very much, Tony. Hi, everyone. So I apologize that you have to deal with somebody with gray hair. Both of the students that led on this work were not able to get visa in time. So it's my pleasure to present their work for you. Okay, so we are looking at evolving graph analytics. So these are graphs that dynamically change over time. So the changes, we look at additions and deletions of edges, but you could generalize those to do vertex additions and deletions or changes in weights and so on. And we would like to go back and answer a sequence of queries over time. And I'll give you an example in a second. So that could involve many snapshots of the evolving graph. And they're similar because these additions and deletions don't tend to completely change the graph. So this has many applications. So this is a recent paper analyzing the evolution of COVID-19 in China using basically a temporal contact tracing graph. So the graph is evolving over time. And then the paper is in 22, so I assume maybe they did the work in 21. They're looking back at the point where the breakout of the pandemic happened, and they're trying to get kind of the same query answered on these multiple snapshots of the graph. So you see over here, this is the number of contacts that they identified on a daily basis inside of the graph, and then they might come back later and say, okay, how many of these contacts were basically from a vulnerable community, or do some more kind of deeper analysis on that. And there are applications for this all over the place, right? So graphs are very useful structure for representing data. They change, and if you want to go back and analyze stuff across these changes, then you're dealing with this evolving graph analytics problem. Okay, so here is a graph before it changes at a certain time t, and then maybe I'm computing shortest path. So maybe this is I want to drive to Seattle right after this session. I want to figure out what is the best route to get there. And then things are changing meanwhile, right? Some edges are added and deleted, and then I end up with a different graph. And then I solve shortest path, and it's something else, and so on, right? I can keep doing that over and over again. So there's a version of this problem called the streaming graph problem, where I'm interested in the shortest path at any given time. So maybe this is for my driving. And then the evolving graph is that going back and doing this historical analysis over much bigger time windows. Okay, so there's two kind of, baseline approaches. One of them, this naive or don't do anything clever approach, where you just solve the query independently on each snapshot, right? So here's the first graph, solve the query, okay, throw all of that away, restart the computation on the updated graph, and then solve the query again, and now you have a new result, and so on. Or you could do incremental recomputation or streaming graphs. I have to be careful that we're relying on Keval's work here, so I have to not make any mistakes. So in this case, basically you have a graph, and you do the computation on it, and now I know like the state of let's say traffic at this point on this transportation graph. And now something's changed. I don't start from scratch. I use the current state of the graph as an approximate initial state. And then I kind of transform it. I do the edge additions and deletions and update the computation based on that, right? So this is the incremental computation or streaming graph problem. So to give you an example, here is a graph, and so this is sort of solving shortest path for this graph, and you can see essentially as you go from left to right, the updates that are happening through different nodes. So you can see A updating C. I mean, I'm computing shortest path from A, and eventually I want to add this edge, and as I add it, I add just an update from A to E, and then that I can propagate that directly over and then solve the problem very quickly. In this case, there was just a single update, and then we converged again. Now, if I'm dealing with deletions, the problem becomes much, much trickier. And in fact, you know, many of the first systems that did streaming graphs ignored deletions. And you know, part of the reason for that, if you remove this edge, so this is, you can think of this as like, you know, equivalent to Bellman-Ford algorithm. Those of you that have done networking maybe heard of the count to infinity problem. So the update that basically that this edge was used on fed into the value for B and the value for E. So when we delete it, it's not so easy to figure out everybody else who's using it. And then these deletion algorithms, I think one of the first was in the Kickstarter system, just kind of go down and track all of the different nodes where the edge that I removed has contributed to. So when you do evaluation, you know, if you look at sort of a streaming graph and then you're doing a bunch of additions, this is the yellow curve down here, whereas an equivalent number of deletions tends to be much, much more expensive, right? So this was the starting point for us thinking about what to do here. Okay, so to recap, we have solve on every snapshot, or do streaming, but now we have to worry about the cost of deletions, or CommonGraph. And the main insight is we're gonna start with the part of the graph that has not changed and extract that as our primary representation. And what does that give us? So as I go from from time t to time t plus 1, I'm deleting the red edges and I'm adding the green edges. So that's a bunch of additions and deletions to go from left to right. If I start somewhere in the middle where I have only the common edges, the blue ones, then I can go to the right by adding the additions, or I can go to the left by adding the deletions, not deleting the deletions, right? So this is our common graph. We solve the computation on it, and then I go to the right by applying this part of the changes, and I can go to the left by applying this part of the changes. And the cool thing is it's a plus D over here instead of a minus D. So deletions are gone. We converted deletions to additions. So we can party, I suppose. And now we can think about generalizing this. So if I have 3 snapshots or more, I can create a common graph across all of them, right? The part that does not change across all of them. But if I want to extend this to many, many snapshots, I think the better way is to sort of create this common graph that encapsulates the common graph between these two, and then identify the common graph between the next two, and then create another common graph. And then if I want, I can create the common graph among those and have like a root common graph. And the cool thing is I'm not actually storing all of these. I store just the base, the top of the hierarchy, and then everything else is just saying, okay, what edges do you add to get to the specific version, whether it's an internal node or one of the leaf nodes. We also broke the sequential dependency. I no longer have to start from the first one and go to the second one and the third one. I can take the shortest path through this structure to get to the instance that I want. Okay, so these are the, to show this mapping, so these are the deletions. Like before, this will be the plus D1 and this is the plus A1. But also, when I delete here, then these edges that got deleted from here have to be added to both of these snapshots. So you see this addition happening 2 places, and you can look at the paper for the algorithm to map from kind of the streaming batches into the structure of the tree, of the triangle, what we call the triangular grid. Okay, so the final piece to the puzzle is now we have this kind of structure. I mean, we use this lattice, but as I mentioned, you don't have to do it. You can put common graphs at any point that you want. You could merge together multiple instances. So the baseline picture is where I sort of successively combine each 2 adjacent instances. And now the question is, if I want the computation on all the instances, so going back to the COVID example, I want the analysis for every snapshot. Then what do I do? One approach is direct hop. Start from the common graph, compute for the first one, compute for the second one, compute for the third one. Notice that we have an option going this way or that way, but it doesn't really matter. But notice that on this side, I am doing this streaming multiple times. And if this is 50 snapshots, then I'm doing it 25 times on the left and 25 times on the right. So there could be a lot of redundancy from this direct hop. So then the natural thing to do is do work sharing. So create this instance of the common graph, which is shared by multiple snapshots, and then you could reach each of them independently. So you stream this part only once, and then this part on the right, you could just do the same way as before. We also noticed that every time you stop at an intermediate graph, there is a little bit of a cost to that because you have to wait for the graph to stabilize. So it tends to be kind of a, a fat tail for the events until they converge. So then, there is a little bit, we'll see under some scenarios, the direct hop ends up being better because we just stream all of these things in a single shot, and then we stabilize only once instead of having to stop in the middle. Okay, so then basically for work sharing, how do we decide what are the intermediate nodes? Again, this is the structure that we used, but we could use any structure that interconnects common graphs to the instances. Well, it turns out that we just have to do basically Steiner tree or minimum spanning tree to figure out the minimum cost pathway that would give us all of the, all of the instances that we want to compute at. And then we modify that only because if you see like this branch, there's I only need one side of it, so there's no benefit for stabilizing at this internal node. So we then end up combining, if I have a straight line, then we combine that into a single batch that we stream together. And we end up with something like this to compute everything, to compute all of the snapshot in a single shot. Okay, so to give you a little bit of an idea about how it works, so we ran this within Kickstarter, modifying Kickstarter, obviously, for 5 different important algorithms. I have to say this is not every algorithm where the delete is more expensive than the addition. It has to have that monotonic property. And then for a number of graphs, and then we used, the graphs are real, but the batches are synthetic, so 50 consecutive snapshots with 75,000 changes between them. So to go from one snapshot to another, a combination of 75,000 additions and deletions. And this is the speed up without taking advantage of the fact that we can do things in parallel still, right? This is the speed, so you essentially cover the tree using sequential computation. And we get something from, like 38%, I think is our lowest, up to 8x improvement before we take advantage of the parallelism. And this seems to be stable across the number of snapshots. So the more snapshots we have, the more we're able to kind of apply these ideas. But it's not, there's still room to improve, and we're working on follow-up work that improves on that. We still have a little bit of redundancy that we can eliminate and hardware support to tap into and things like that. There is a little bit of sensitivity to the batch size, not so much the comparison to the add plus delete, but that there is a switch over between the direct hop and the work sharing, right? And that happens because of this cost of stopping. So if the number of batches is small, then it tends to become like, less efficient to stop. But if the batch sizes are high, then work sharing ends up helping us, right? So notice that we keep the number, in this experiment, we keep the number of updates the same, but we split them over more or less snapshots. If we have like more deletions than additions, we end up benefiting more, as you would expect. So as you go to the right, the speed up increases as you have more deletions because deletions are expensive and Kickstarter slows down, and deletions don't hurt us, they become additions. And finally, my final result is kind of thinking about that parallelism idea. We're not, we're kind of estimating how much it could help. So once you're doing, let's say, direct hop, then you can take all of these kind of jobs to go to the individual leaves and then parallelize them. They're completely independent at that point. So if we did that and we took the time of the longest execution, so that's kind of an upper bound on the type of speed up that we get, and we end up getting on 50 snapshots between 51 and 400x speed up over Kickstarter for those things. I have to say this is sort of back of the envelope computation. This is not we built a system and it runs that way. It's just kind of giving an idea about the opportunity that's still there on the table. Okay, so that's basically all I have. New abstraction for streaming graph processing. Main idea is it converts deletes to additions. Representation is super neat, super compact. It doesn't, we're not actually creating all of these things. They're all within the same representation. Exposes parallelism and makes a lot of sense if you want to do evolving graph processing. Thank you.